Take any whole number, say 6. Now start listing factorials. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and so on, each one the product of everything up to it. Here is the question. What is the first factorial on that list that 6 divides evenly? 1 factorial is 1. 6 does not divide 1. 2 factorial is 2. 6 does not divide 2 either. 3 factorial is 6, and 6 divides 6 exactly. So the first factorial that 6 fits into is the third one. We write that as the answer for 6 is 3. That little test has a name. For a number, look for the smallest factorial that it divides, and record which factorial that was. The number you record is called the Kempner function, also known as the Smarandache function. For 6 it equals 3, because 3 factorial is the first factorial that swallows 6 whole. We started at 1 for the number 1, since 1 divides everything, including 1 factorial. So the rule is simple to state. Take a number, march up the factorials, and stop at the first one your number divides. The position where you stop is the whole story. For the rest of this video, we chase what that position does. Let us run the test on the first several numbers, and just watch the answers. For 2, the smallest factorial divisible by 2 is 2 factorial, which is 2, so 2 gives 2. For 3, 3 factorial is the first one divisible by 3, so 3 gives 3. For 5, likewise 5. These are easy, the answer just equals the number. Then 4 breaks the easy pattern in a small way. 4 does not divide 3 factorial, because 3 factorial is 6, and 6 is not a multiple of 4. You are forced all the way up to 4 factorial, which is 24, and 24 is divisible by 4. So 4 also gives 4, but for a different reason than 3 did. Hold on to 4, it will turn out to be special later, and then 6 surprises you the other direction. 6 gives 3, not 6, because 3 factorial already contains a 2 and a 3, and their product is 6. So 6 slips into a much earlier factorial than its own size would suggest. Some numbers land early, some are forced late, and the answers jump around. To see the pattern behind the jumping, we have to look at what a factorial is actually made of. Here is the first clean rule, and it is about the prime numbers. For a prime, the answer always equals the prime itself. Take 7. A factorial is a product of the counting numbers, 1 times 2 times 3, and onward. The prime 7 cannot appear as a factor until you actually multiply by 7. Nothing smaller has a 7 hiding inside it. So no factorial before 7 factorial is divisible by 7, and 7 factorial is. The answer for 7 is exactly 7. The same reasoning works for every prime. 11 first shows up as a factor at 11 factorial, so 11 gives 11. 13 gives 13. A prime is a number with no smaller factors to borrow, so it has to wait for its own turn in the product. Every prime gives back itself. If you picture the answers on a graph, with the input running along the bottom and the answer going up, this says something striking. Every prime sits exactly on the diagonal line where the answer equals the input. The primes all land on that perfect 45-degree line. That single fact is going to become a way of seeing the primes, and we will draw the full picture soon. Primes are settled. The next building block is a prime multiplied by itself. Powers like 4, 8, 9, 25. For these we need to count more carefully. Take 8, which is 2 times 2 times 2. To have 8 divide a factorial, the factorial needs 3 factors of 2 inside it. So the real question is how many 2's a factorial contains. Count them. 2 factorial has 1 2. 3 factorial still has just 1, but 4 factorial brings in the number 4, which is itself 2 2's, so the count jumps from 1 straight to 3. 3 factors of 2, exactly what 8 needs. So 8 gives 4. There is a tidy formula for this count, due to Legendre. The number of times a prime divides a factorial is found by adding up how many multiples of the prime, then the prime squared, then its cube, appear below the cutoff. It is just an organized way of counting the same factors. Run it for 9, which is 3 times 3, and needs 2 factors of 3. You do not reach 2 3's until 6 factorial, because 6 brings in a second multiple of 3. so 9 gives 6. Every prime power is handled by this one counting idea. Now we can handle any number at all, because every number is a product of prime powers, and the pieces barely interact. Here is the rule. Break the number into its prime power parts. Work out the answer for each part on its own. Then take the largest of those answers. That largest one is the answer for the whole number. The reason is that a factorial big enough to contain the most demanding piece automatically contains all the easier pieces too. Try 12. It splits into 4 and 3. 4 on its own gives 4. 3 on its own gives 3. Take the larger, and 12 gives 4. Check it directly. 4 factorial is 24, and 12 divides 24, while 3 factorial is only 6, which 12 does not divide. It works. Try a bigger one, 100. 100 is 4 times 25. 4 gives 4, as we saw. 25 is 5 times 5, and it needs 2 factors of 5, which first happens at 10 factorial, because 10 brings in the second multiple of 5, so 25 gives 10. Take the larger of 4, and 10, and 100 gives 10. And sure enough, 10 factorial is the first factorial that 100 divides. One rule, the maximum over the prime power pieces, cracks every number. Now let us draw the whole thing and look at its shape. Put the input along the bottom, from 1 up to 60, and the answer up the side on the same scale. Plot a point for every number. 2 things jump out. First, no point ever rises above the diagonal, because the answer is never larger than the number itself. Every number divides its own factorial, so its answer is at most its own size. The whole cloud lives on or below that diagonal line. Second, and this is the beautiful part, which points actually touch the diagonal, the primes. 2, 3, 5, 7, 11, 13, and all the rest sit right on the line where the answer equals the input, exactly as we argued. Everything else, the composite numbers, falls below, often far below, because they borrow small factors and slip into early factorials. The graph sorts the numbers for you. Sit on the diagonal, you are prime. Fall below it, you are composite. The function quietly detects the primes. Almost. There is exactly one cheat on that diagonal, and we already met it. Look carefully at the point for 4. It sits on the diagonal too, because 4 gives 4, yet 4 is not prime. 4 is the one composite number whose answer equals itself. So the clean statement needs a single repair. Why is 4 alone in this? Because for every composite number bigger than 4, the number divides the factorial just below it. Here is the idea. A composite past 4 can be split into 2 different factors, both smaller than the number, and both of those factors already appear separately among the terms below it in the factorial. Their product is therefore inside that earlier factorial, so the number divides it, and the answer comes in strictly below the number. Only 4 is too small for that trick to have room to work, since 4 is 2 times 2, and there is just one 2 to go around down there. So the corrected rule is exact. For any number from 5 upward, the answer equals the number if and only if the number is prime. Set aside the lonely 4, and sitting on the diagonal is precisely the same thing as being a prime. A test built from nothing but factorials and divisibility recognizes the primes on sight. One more thing about the shape of these answers, and it is a result of Paul Erdos. We saw composites fall below the diagonal. How far below? For the vast majority of numbers, the answer is simply the largest prime factor. Take 12. Its prime factors are 2 and 3. The largest is 3, but its answer is 4, so 12 is one of the exceptions, tripped up by its repeated 2. Most numbers are not like that. Take a number like 51, which is 3 times 17. 17 is its largest prime. 17 has no repeats to worry about, and the answer is exactly 17. Count how often the answer is just the largest prime factor. Among the numbers up to 1,000, it already happens for about 7 and 8 of them, and Erdos proved that, as you go further, the exceptions become vanishingly rare. For almost every number, this elaborate factorial test collapses to something plain. Find the biggest prime dividing the number, and that is your answer. The prime powers, like 4 and 8 and 9, are the only troublemakers, and they thin out. Underneath the jumpy graph is an almost boringly simple truth for nearly all numbers. So here is the whole picture, in order. Start with a number and march up the factorials until one of them is divisible by your number. The factorial where you stop is the whole function. It never exceeds your number, because a number always divides its own factorial. It equals the number exactly on the primes, and, apart from the single stubborn 4, only on the primes, so sitting on the diagonal is the same as being prime. And for almost every number, it is nothing more than the largest prime factor in disguise. None of this changes what the primes are, but it gives you a new way to see them. Line the numbers up, ask each one for the smallest factorial it divides, and the primes are exactly the ones that answer with themselves. The smallest factorial that swallows a number knows, almost by accident, whether that number was prime all along.